In this video, we're going to learn about how to use the mole with compounds. So let's start with water, nice simple compound. We know that in one molecule of water, there is one oxygen atom, but there are twice as many hydrogen atoms. There are two H atoms for every one water molecule. So if we were to scale this up and we were to take, say, a dozen water molecules, then there would be 1 dozen oxygen atoms and 2 dozen hydrogen atoms. Well, if we made this even bigger and scaled it up to a mole, there would be 1 mole of oxygen atoms per mole of water, but there would be 2 moles of hydrogen atoms per mole of water. And if we wanted to talk in terms of mass, then the mass of a mole of water would be equal to the mass of a mole of oxygen atoms plus the mass of 2 moles of hydrogen atoms. So the mole of oxygen atoms weighs 16.00 grams, and the 2 moles of H atoms, they weigh, let's say, 2 times 1.01 grams. And if I add these together, 2.02 plus 16.00 gives us 18.02 grams of water for every mole of water. That would be known as the molar mass of water. And this is just taking the atomic mass of oxygen and the atomic mass of hydrogen, multiplying hydrogen's atomic mass by 2, since there are 2 hydrogens per water, and then just adding those together. So let's do a bit of a practice problem here. What's the molar mass of Na2O? Well, Na2O, we have Na, and we have O. And if I look on the periodic table, Na weighs 23.00 grams per mole, and there's 2 of them. And then O weighs 16.00 grams per mole, but there's only 1 of them. So we end up with 46.00 grams of sodium plus 16.00 grams of oxygen, and we add them up and we get 62.00 grams per mole. And that is the molar mass of Na2O, sodium oxide. So if we would like to conduct an experiment that requires 2 moles, 2.00 moles of Na2O, we could figure out the mass of sodium oxide, Na2O, that is necessary, the same way that we would work with just elements. But instead of looking up the element on the periodic table and multiplying that molar mass by the number of moles, we do have the second step, or I should say the initial step, of figuring out this 62.00 grams per mole. So we have 2.00 moles of Na2O. And we're going to multiply this by 62.00 grams for every 1 mole of sodium oxide. And this brings us to 124 grams. That's a 2 there, 124 grams of Na2O. And just for clarity, there are 3 sig figs in my moles. There are 4 sig figs in the molar mass. There are 3 sig figs. There should be 3 sig figs in the answer, and there are. And again, if you were problem solving all at the same time, if you only had this question and not what is the molar mass of Na2O, of course, you would need to do this calculation. You would need to do that down here as an initial step before you do your 2 moles times 62 grams per mole. All right, let's try another. We have a sample of carbon dioxide that weighs 22.0 grams. And in this case, we're going to molecules of carbon dioxide. So actually, we need to use dimensional analysis to go first to moles, and then from moles to molecules. Trouble is, the molar mass of carbon dioxide, this isn't as simple as looking up one thing on the periodic table. We have to do this off to the side. So for CO2, we need carbon and oxygen. The oxygen weighs 16.00 grams per mole, and the carbon weighs 12.01 grams per mole. There's only one carbon, but there are 2 oxygens. So, whoops, we have 12.01 grams per mole that are just the carbon, and 32.00 grams of oxygen. And this adds up to 44.01 grams of CO2 for every 1 mole. So from here, I can take that 22.0 grams of carbon dioxide, and I will multiply that by a conversion factor. I'll multiply that by 1 mole for every 44.01 grams. Notice our grams cancel out. However, we are not all the way yet. We only are at moles of carbon dioxide, and we want the molecules of carbon dioxide. So what we need to do is multiply by Avogadro's number, which is 6.02 times 10 to the 23rd molecules. For every 1 mole. And that brings us to, let's see, our moles cancel out and we're at molecules. Notice that molecules, we can use Avogadro's number for molecules just as we could for atoms. But anyway, there are this many molecules for every mole, and what we have 22 times 1 over 44 is a half of 6.02 times 10 to the 23rd. So we have 3.01 times 10 to the 23rd molecules. That should be a 23rd molecules of CO2 that are in this 22.0 gram sample of carbon dioxide. So there we go. And as a little bit of an extension, we could go to this question: how many atoms of carbon and oxygen are in this sample? And what we can do is we could say that we have 22.0 grams of carbon dioxide times 1 mole. And I'm actually going to put the CO2 here just to clarify. For every 44.01 grams of carbon dioxide. And now I'm going to multiply this by the fact that there should be 1 mole of carbon for every 1 mole of carbon dioxide. So from here, I can say that there are 6.02 times 10 to the 23rd atoms for every 1 mole. And this brings us to 3.01 times 10 to the 23rd atoms of carbon. So that would be the number of atoms in in 22.0 grams of carbon dioxide. And notice that they're the same number of atoms of carbon as there are molecules of carbon dioxide. That's because there's 1 atom of carbon for every molecule of carbon dioxide. And this is something that I did out rather rigorously here, but you could almost intuitively take it from this point. So from here, I also could say that instead of multiplying by 1 mole of carbon per mole of carbon dioxide, we could say that there are 2 moles of oxygen for every 1 mole of CO2, carbon dioxide. And from here, we could also multiply it by Avogadro's number, 6.02 times 10 to the 23rd atoms for every 1 mole. And this comes out to 6.02 times 10 to the 23rd atoms of O. And there we are. Hope this video has been helpful. Please feel free to leave any questions or comments in the comment section below. Thank you for watching.